my presentation is I want to talk about this paper here. Um, it's the deduction rule in linear and near-linear proof simulations. Um, the background information needed to understand this paper isn't all that complicated, so I figured I would introduce uh, the parts that are needed. Um, so that's what this slide shows for. To start out with, um, we're talking about proofs and whatever else, right? So what proofs are is uh, the way we talk about proofs is we talk about something being either true or false, and that's what this set is here. It's the set of true and false statements. Right? If something is true, you take it to be absolutely true for every interpretation. If it's false, we don't really care about it. Um, so here's a set here, the set of booleans. What can we do with booleans? We can define functions on them. An example of a Boolean function is the negation function that takes one Boolean argument and then returns the opposite of what it got. So not false is true and not true is false and so on. So here's a pretty good example of a Boolean function. Another one is arrow, uh, as I call it, but it's also known as implication. Um, and so what this implication operator is trying to say is if A is true, then B is true, right? So if we have that A is true, then we also have to have that B is true. So if you have A is true and B is true, then A implies B is true, right? Um, if A is false and B is false, that doesn't break our assumption that if A is true, then B is true. So that's also true. Actually, the only case where if A is true, then B is true is false is if A is true and B is false, because that contradicts our definition of implication, right? So this is arrow. Um, I'm going to write a lot of arrows later. So when I write A arrow, B arrow, C arrow, D, assume it associates to the right. So A implies, B implies, C implies, D is read as A implies, B implies, C implies D. Okay. Um, cool. Here's a few more Boolean operators and an or. Um, if A and B is true, then A and B is true. Right? That's what this guy says. For every other case, A and B is false. Um, our other operator here, then A or B is true. Right? So that lines up with this truth table here. Right? But what's interesting about or and is that you can write them in terms of just negation and implication here, right? So if you look at these truth tables, um, this column here is the same thing as this column here, right? So if we have, yeah, so you can define A or B to be this composition of arrow and negation. Similarly, for A and B, you can define it to be this composition of arrow and negation, right? That's kind of neat. What other functions can we define in just in terms of arrow and negation? Well, it turns out it's all of them. Uh, here's a sketch of the functional completeness proof for arrow and negation. You can construct every one variable binary function with arrow and not. There's only four of them. You have the constant true function that returns true for every input. The constant false function, which is false for every input. You have negation and you have identity. And define all of those just in terms of arrow and not. right?
Sorry, what do you mean by one variable? Aren't these two variables, or is that what you meant by binary? You say one
Right.
variable.
So I'll go grab a toy that I'm going to talk about later. Um, so for example, if I write this, there's only one variable, right?
Okay,
Because
gotcha.
yeah, yeah. So this is a function of one variable, but it represents the constant true function, right? This is how you would do false, um, right? Here's how you do identity, um, not A, and then not A is of course just the negation. So those are all four of the one variable binary functions. Um, as we saw above, and or can be just constructed from implication and negation. That's these two columns here. Uh, so that's good. Now, this proof is by induction on the number of variables in your Boolean function, or the number of variables that your Boolean function takes. So, suppose you can construct any binary function of n variables. Then you can write any n plus one variable binary function as this mess. All right. Um, so the way this works is um, if we look at these tables here, and you look at this b here, notice that um, well, first of all, since there's two variables for these functions over here, that means there are two times two or four possibilities or four possible inputs, right? In general, for an n variable Boolean function, you can have two to the n inputs. Um, so every single time you add a variable, you double the number of possible inputs to your function. Right? What this is saying is um, you can write any n plus one binary function as this case here, which is for any assignment of a0 to an, if an plus one is true, then you get this side of the function, right? And if an is false, you get this side of the function. So we're conditioning on an plus one, if that made any sense.
Yeah, it makes sense. You're just duplicating all of the conditions of like the previous thing, and then just doing like if statements based on the thing that you're appending on.
Yeah, yeah. And my claim is that you can write any n plus one variable binary function in this way. All right. So that's my functional completeness sketch. Now, let's go back to the definition of A implies B, or A arrow B. Um, specifically, if you just look at this last column here, um, notice that when A implies B is true and A is true, B necessarily has to be true, right? um, and that's just by looking at the table here. Um, so we can turn this into a general rule called modus ponens. If A implies B is true and A is true, then B has to be true. All right. Does that make sense?
Yep.
Okay. So that's like an interesting fact. All right. Moving on. Um, there are a few special binary functions called tautologies. They're always true. So if you map out the truth table, as they're called, where you explicitly show every possible input in a table and every output in a table, these functions will always be true regardless of the input. Um, and that's where I introduced this cool toy that I used earlier. Um, that's not what I wanted. Uh, it's not letting me copy it. So Put it this way. Okay. Um, this cool website here will give you the entire truth table for a binary function you pass it. It takes all sorts of syntax, basically uh, everything that's common. Every common representation for Boolean operators it'll accept. Um, I'm having no luck copy pasting things. All right, you're just gonna have to trust me that when you put these into this tool here, it'll give you back a truth table, and they're always true as the output. Right now, we can define one of the actors or one of the paper that I want to talk about talks about. Um, so, what is a Hilbert system? A Hilbert system is, if we go to the Wikipedia page, it's a I don't want to read that. It's a system that has one inference rule, this guy here, its most opponent, and a large number of axioms, which look like this, and it lets you prove things. All right. A proof in a Hilbert system is a a bunch of lines that either reference one of these what are called axioms, things you assume to be true, and or the line can be the inference rule where you inference on two previous lines and you get something back. Um, Here's an example. Here's a so-called Hilbert style proof of A implies B. Um, so the first line here says that we can prove A implies A implies A using axiom one here. These are actually schematic axioms, as they're called. You can replace A and B in these with any uh, propositional statement. In this case, just assume it's some composition of arrow and not, or just a variable. All right. So we can prove A implies A implies A by this A1 axiom by picking A to be A and B to be A. All right. Similarly, by A1, we can prove that A implies A implies A implies A, right? By picking B to be A implies A, all right? And then you can also prove this by uh, A2, and then this is how you'd use the modus ponens rule, all right? Uh, so we know that 3 is true, and 3 is of the form this implies that, so we know that this is true, right? Does that check out for the modus ponens rule?
Yes.
All right, and then from here we can prove A implies A using modus ponens on three. Yeah, modus ponens on 4 and 1. That's neat. So one special thing about Hilbert systems is that it turns out that everything you can prove in this specific Hilbert system with these assumptions is a tautology. Right. So A implies A. We saw earlier that this is a tautology. Um, And it turns out that if A is a tautology and B is a tautology, then modus ponens will return a tautology. Or sorry, if A implies B is a tautology and A is a tautology, then if you use modus ponens on those two statements, you get back a tautology. All right, so that's neat. If you can prove it in a Hilbert system, it's a tautology. Okay, um, so what's something we can prove about a Hilbert system? One of the main theorems for Hilbert systems is called the deduction theorem. All right, I'm gonna define a new structure here. Uh, this this here is called TAC, I don't know what this one's called, but anyways, what this says is from these assumptions, you can derive B means if you assume H0 through Hn are true, then you can derive B. Yeah. So if you add can derive this hypothesis to the Hilbert system for every one of these hypotheses, and you can prove B, that's what this syntax here is trying to say. So if from these hypotheses you can derive C, so sorry, now let me define the deduction theorem. What the deduction theorem says is if from these hypotheses you can derive C, then from one fewer hypotheses you can derive this hypothesis implies C, all right? And you can apply this inductively to get like to turn a statement with say n hypotheses into a statement with n minus one hypotheses, but it proves Hn implies C. Did that make any sense?
I mean, it sounds like you're just saying like if you like the set of things that implies C, but like the set of all but one things that imply C implies the missing thing implies C, which to me makes
Yes.
sense.
Yeah. Actually, you can apply this inductively and then get rid of all of your assumptions.
Yeah, so it would just be like a long chain of implies, right?
Yeah. So we're gonna sketch the special case where you only have one assumption. So we will show if from H you can derive Q, then you can derive H implies Q. All right. By induction on proof steps. So what is a proof step? It's either so this step one references an axiom, and this step four references the only inference rule we have, which is modus ponens. All right. So those are the two possible forms of a proof step. So we have to break into cases on that. Uh, so for our base case, we either have that proof step Li is of the form can derive H, right? Then substitute it with H implies H. H implies H is a tautology, and I showed that you can prove it earlier. Um, so that's the justification for this step here. Um, if the if line is an axiom, uh, then line I is of the form can derive A, right? And then what I'd have you do, our goal is to prove H implies A, right? So how you do that is use A1.
I just lost your audio. I don't know if that's true for anybody else, but I can't hear you all of a sudden. Hello? Am I the only one here? Can you hear me? What?
All right. Does
Apologies.
that make sense to everyone? This is the base case of our induction. Um, so these are the two steps that you can use without prior lines, right? And they are either can derive H, where H is a hypothesis. So you just replace it with H implies H, which is a tautology, and I showed that we proved it earlier. And if our goal is to show from can derive A, H implies can derive A, right? Um, so if line I is an axiom, then add the lines can derive H implies, or sorry, A implies H implies A. Uh, with our first assumption, A1, and then just do modus ponens on this line in the axiom, as we can always prove the axiom. All right, so that's the base case of our inductive proof. Now, what do they call it? The inductive step, right? If line I is modus ponens on line J and line K, then line I is of the form can derive B, and line J is of the form can derive A implies B, right? And K is of the form can derive A. Yep. All right. So by the induction hypothesis, we can derive that H implies A implies B, and we can derive that H implies A because lines J and K happen before line I, right? Um, so our goal is to show that H implies B. Trying to show H implies B. How do you do that? Um, with axiom 2, which is of this form, um, for appropriate assignments of A and B, you can get this mass, right? Um, but notice that line F is of the form can derive H implies A implies B. So you can get this mass by applying modus ponens. And then line A is of the form H implies A. So you can get this mass by modus ponens again, which is what we wanted to show. Is arrow left or right associative? It's right associative. Yeah. Okay. So yeah, that's the proof sketch of the deduction theorem. I'll link a few textbooks that go more into detail if you want, but um, just note that if you have assumptions, you can always get rid of the assumption by turning it into that assumption implies C, right? And this is actually how most proofs, I think, in math are gone about. You assume something's true, and then later on, use the deduction theorem to say that that thing implies something else, right? All right. So that's what a Hilbert system is. Um, moving on. The other thing that the paper I want to talk about discusses are what are called nested deduction systems, or uh, another way to put it is a natural deduction system. That's what the syntax here with the bar is. I can explain that. So this bar says that if the thing above the bar is true, then the thing below the bar is true. Isn't that great? So these are the rules for a very simple nested deduction system that forces you to use assumptions as they're taken. Okay. So what this first rule says is that if A is an axiom of your system, then from this context, which may be empty, you can derive A. This context is just a list of assumptions, all right? Um, here's another rule that says if you have a list of assumptions, if you add A as an assumption, you can derive A. This is the weakening rule because it makes this context weaker. You have more assumptions. Well, can't remember if it's called the weakening rule or the strengthening rule. It's one of the two. Um, this rule here is called deduction. if from this context with this assumption you can derive B, then from this context you can derive A implies B. Um, and then the last rule, which looks kind of gross, is if you have a context where you can derive A implies B, and you have another context where you can derive A, and uh, the first context is a prefix of this big context, and the second context is also a prefix of this big context. You can, from the big context, you can derive B.
What do you mean by
Right?
prefix?
What do I mean by prefix? I mean that so a context is just a list of hypotheses, right? Um, what I mean by prefix is I mean every hypothesis that's in gamma 1 at index I is in gamma at index I.
So they're
That
just
check out?
Are we just saying subsets of?
So the order does matter uh, because this is a particular kind of deduction system where you can only use the topmost assumption on the context.
Yeah. So as
So think
MultiTube says in the chat, okay, so it's not simply the union of gamma 1 and gamma 2 in the pure set theoretic sense, which is what I was thinking too.
you can think of it as a list though. So gamma 1 is a list and sigma here is a list. Then if you concatenate those two, they equal this big context here. And if you concatenate gamma 2 with pi, you get this big context here for some pi and some sigma, right? By prefix, I mean it's a prefix of the list of assumptions. Does that check out?
Yes, like the list of assumptions, like gamma starts with gamma 1 and it also starts with gamma 2.
Yeah,
Why is this construction here? I'm failing to see the utility of this big blob.
of this
Like,
big blob.
yeah,
Um,
that equation, like, well, it seems very weird. Like, why are we considering prefixes?
so this is a particular kind of deduction system that only lets you talk about the assumption on the top of the stack. There's like a general one that lets you talk about any assumption in the context. Um, but if you can only talk about the guy that's on the top of the context, then you need to have some way of
Okay, I think
weakening your context.
right. So we're
Right?
popping things off the top and then applying that somehow. And
Yeah, something like that.
okay,
Right. I think the paper goes into this a bit more in depth. Uh, yeah, so this here is a system that just lets you use any hypothesis that's in the context. Um, yeah. And then they move on to this particular slightly weaker system where you can only talk about the topmost hypothesis on the stack. All right. Um, I could probably link that too.
when you say weaker, you actually mean it's weaker in the sense of it can't derive as many theorems given some set of axioms.
Um, by weaker, I mean uh, you can prove the same statements, but this one is at most quadratically slower than the other one.
Oh, okay, gotcha. Cool.
Slower is in proof length, right? Um, all right, maybe an example, all right? So here's a proof. This is by the weakening rule. Uh, yeah, I don't know if I named that correctly. It might just be the strengthening rule. I don't remember. Um, So by this rule here, we can say that from context A, we can derive A, right? And then by uh, this rule here, we have A implies A. So, sorry, from A, we can derive A. So from the empty context, we can derive A implies A, right? That's what the deduction rule does. Um, Now, step 3 here is we use the apply rule. Uh, yeah, okay. So we use the apply rule on step 2 and step 1. So step 2 has an empty context, so that's automatically a prefix of this context, right? Um, so it follows this rule here because it's a prefix of our big context. And also notice that A is a prefix of this context. So that satisfies this bit here. Um, and then it's just modus ponens on A implies A and A, which gives us A, right? Does that check out?
Yeah, I think so.
All right. Um, and then by the deduction rule, we can derive B implies A. And then by the deduction rule again, we can derive A implies B implies A, right? You might recognize this guy from the Hilbert system earlier. Um, where's that at? Yeah, axiom 1. Yeah, all right. Where am I at? So that's an interesting proof here. Here's another one. I might not go into as much detail here, but prove this by a week. You can prove this also by a week. Uh, yeah, same thing. And then you can apply this guy to this guy because this is a prefix of this context, and this is also a prefix of this context. So you can get B implies C, and then uh, if we apply A implies B to A, you can get a B. And then if we apply B to B implies C, you can get a C, right? And then from there, you can just use the deduction theorem like 4 times and end up with this guy, which you may recognize from the Hilbert system earlier. Sign in. Yeah, axiom 2. All right. So that's interesting. We can prove A implies B implies A, and we can prove A implies B implies C implies whatever else. Um, yeah. So in general, if you can prove it in the original Hilbert system, you can prove it in this nested deduction system if you assume that what is it? A3 is also an axiom of the nested deduction system. Right? That check out?
I think so.
Because we can prove both of the other axioms using this system, and it also has a construct that lets you basically do modus ponens because they both have an empty context. Right? All right. What about the other direction? Can you simulate a nested deduction style proof in a Hilbert system? Um, the proof I gave earlier for the deduction theorem with with one assumption lets you turn a proof with one assumption into a proof with no assumptions, but it's a constant amount longer, right? And that's just for one argument. So let's say you have one assumption. So if you have more than one assumption and you just naively do that process over and over again, you end up with n to the d, big O of n to the d, where d is the number of hypotheses, right? So that's terribly slow. There's another method that's kind of common, that's big O of n squared. The way that's done is it's done with bracket abstraction, which I'll talk about later. But this cool paper that I want to discuss is a way to convert a nested deduction style proof into a Hilbert style proof in nearly linear space. Right. So that's what we're going to be talking about. So how do
When
they
you
do
say
it?
linear space, do you still mean linear proof length, or are we saying like the actual
Yeah.
algorithm? Oh, okay, gotcha.
Linear proof length. The algorithm is also, well, you can come up with an effective way to do it that's also linear or nearly linear. All right. So this is the deduction theorem, or sorry, this is an example of using the deduction theorem with one hypothesis in a Hilbert style system. Yeah. So this step here is of the form can derive a hypothesis. So you just use the construction for proving C implies C, which is that mess. Right? If you have a step of the form modus ponens on 2 and 1 with, say, more than one hypothesis, then you just yeah, you do this mess. Right? So this step here is of the form can derive the topmost hypothesis. So you just use a proof like this to prove A implies A from the remaining hypotheses and so on. Um, yeah. Again, it's not terribly difficult. Um, we're just following this process that I described earlier for the deduction theorem with one assumption. So converting proofs like this into proofs like this isn't too terrible. Um, what the paper says you do instead is if you have a proof of the form from this context, you can derive sigma 1. It's another uh, inductive construction where you have some base cases and then you have this inductive step here. Right? So let's say that sigma I is an axiom, then what the paper would have you do is you would replace it with um, the conjunction of the context implies sigma I, where the conjunction of the context is defined in this way. Right? So let's say gamma is in the context, right? And gamma 0 is at the beginning of the context, then the conjunction of the context is just gamma 0 and gamma 1 and gamma 2 and so on. But notice it associates to the left. That's important, and we'll get to that later. So yeah, similarly to the construction we did earlier, where we proved the deduction theorem for one assumption. Um, in the case where the line was just an instance of an axiom, you just replace it with something implies that axiom. Right? Any questions about the syntax here or whatever else? I feel like I'm getting a little rambly.
I think I'm following, but I'm not sure how this is gonna land exactly. So maybe just continue, and then I might have a few.
All right. So, um, I should probably restate what we're trying to do. We're trying to turn a proof from a nested deduction style proof, which has a context, into a Hilbert style proof, which doesn't have a context. So instead of from gamma 1, we can derive sigma 1 or whatever. We really want just gamma 0 to, sorry, gamma 0 implies gamma 1 implies gamma 2 implies sigma I. So we're trying to turn a proof of this form into a Hilbert style proof of this form. Right? So what the paper would have you do is for the case where sigma 1 is an instance of an axiom, replace it with the conjunction of uh, gamma implies sigma I, which you can do with A1. Right? If sigma I is a hypothesis, right, then what the paper would have you do is it would have you replace that line with the conjunction of gamma from 0 to j implies gamma j, right? And how do we prove this statement? Well, it's another tautology. Note that this is a tautology. A and B implies B is a tautology. Um, so we can prove it in our Hilbert system, right? So the idea here is that A is the conjunction of gamma from 0 to j minus 1, and B here is gamma j, implies gamma j. So that's what the paper would have you replace it with. I'm going to skip that step for now. Now, suppose sigma I is a deduction step. We talked about the deduction step earlier, right? If you have a context with A at the end of it and you can derive B, then from just this context, you can derive A implies B, right? And how do you do that? You would right. So notice that line I is of the form uh, from this assumption, from this context gamma, with this extra assumption gamma n, we can derive sigma I. It takes this line and then turns it into this line here, which is from gamma, we can derive we can derive gamma n implies sigma I, right? And what the paper would have you do is replace that line with from this context, um, gamma from 0 to n minus 1 and gamma n. So this is just the conjunction of the context gamma. Um, Having a hard time explaining this. All right. So our assumption is we have a proof of this form. Or sorry, there's a line somewhere that has this form, and by the induction hypothesis, we can write that in this form where we have a conjunction of the context implies sigma I, right? So we have a line somewhere that looks like this. So through our process, we can turn it into a line that looks like this. where we have a conjunction of context implies sigma I, right? And it turns out that this is just another instance of a tautology where um, A and B implies C. So this is just another tautology that you can use. So we can prove this line by the induction hypothesis, and this is a tautology. So by modus ponens, we can prove this, right? Which is exactly what we wanted to show. Does that make sense?
I'm I can't help but wonder why is there a reason that people study like systems of deduction where you can't just like have a pool of usable information at any given point in time? Like it seems like we're handicapping ourselves a lot. And I mean, I guess the result is cool that you can still like prove the same stuff and perhaps even with the same amount of space, but like is this useful somewhere?
It's interesting to me because the you can write so-called proof checkers that are really small and therefore likely don't have any errors, right?
Uh-huh.
For example, the lean four checker,
Yeah.
according to my sources, has like 6,000 lines of C or something like that.
Uh-huh.
I imagine there's space for random bugs to show up in that.
In the proof checker,
Yeah.
is this what it's doing under the hood?
No, it's doing something similar to this, where you have a natural deduction style. Um,
Okay.
yeah.
Gotcha. So wait,
All
what do you
right.
mean then when you say it's doing this? It's doing. It could have bugs in. Sure, there could be bugs in lean, but does that relate to proof length?
Does it relate to proof length? What this paper showed is that you can turn any deduction style proof into a very similarly sized Hilbert style proof, right?
Yeah.
So if the size of your proof is related to how fast you can check it, which I'm pretty sure it is,
Mm-hmm.
it means that one system isn't asymptotically better than the other, or
Right.
asymptotically better by very much,
So we're
right?
concerned with what how we should be representing our proofs in the first place in like computational systems. Is that kind of the goal?
Something like that, yeah.
Okay. So so is the takeaway here that neither one is better than the other? Is that kind of the point?
Um, yeah,
Or
that's where I'm trying to get to. Yeah.
gotcha.
All right. Do we have any questions about this so far? I'm trying to describe a process by which you can turn a proof of this form into a proof of this form.
Yeah, I'm not gonna lie. I lost you in the details there somewhere along the way. I think I,
Yeah,
I think I followed you on every individual step, but I could not write that out.
yeah. Um, Maybe it's best to leave most of the details to the paper where they do it the right way.
Yeah,
Anyways,
possibly.
um, so the eventually the paper gets to this part here, which is the important part for proof length, right? All of these other steps have a size that is constant in, sorry, have only add a constant number of lines, all right? This step here, it's not clear that it adds only a constant number of lines because you need to prove these, what are called transport lemmas. Um, right. So what this step requires is it needs these two proofs here which is of the form from this bigger context, we can show that this smaller context is true. For both of the contexts in the in the apply rule here, which is context 1 and context 2. So what does that look like? All it's trying to show is that from if we know that A and B and C and so on is true, then we can derive that some prefix of this context is also true. So yeah, all right. So that's what one of these transport lemmas looks like. We just want to show that from A and B and C, if this whole statement is true, then we can show that just A and B is true. It turns out that uh, this guy here is a tautology. It's the and left tautology. So you can just iteratively apply this to get your a proof of your smaller context. Does that make sense?
Do we know how many layers we're gonna have to be peeling off there? Because it seems like that could be variable or like
Yeah,
arbitrary.
yeah. That's the interesting part. You can have, let's say, your proof has n lines. You can have at most n layers. Okay? So we'd have to peel back at most n layers for this one step, right? So you might think that this gives you an n squared algorithm, right? But what the paper showed is that you can, since this is the hard part, we just need a way to make this hard part uh, only cost a constant amount, all right? So what they did is they noticed that you can turn proofs of this form, right, where it's a nested deduction system and you take hypotheses. Um, so let's say that this is a proof in a nested deduction style system. What you can do is you can make a tree where, let's say, A here is the beginning of the context. And every time you add a new assumption to this context that starts with A, you just draw a line to the new assumption, right? And everything you can prove from that assumption. So this tree here represents this proof. You see the, does that make sense?
Yeah. Okay. So let me just check that I'm understanding everything. You're saying first of all both that it's going to be constant time checking and it's going to be a constant size proof translation. But what we're showing right here is the constant checking, constant time checking part, right? This is
um,
like the structure that we would be building internally to the computer when
so
we're
we need to show that we can construct all of these transport lemmas in a way that isn't terribly slow. Um, we don't want to add n lines for every modus ponens rule because then we'd end up with big O of n squared, right?
right. Yep.
We can add at most something that is almost linear uh, in lines for every single one, or sorry.
Wait, the tree is going to allow us to do something linear in line count?
Uh, yeah, we're getting there.
Okay, sorry. Continue.
All right. So the idea is we make a structure that is almost linear in the size of the proof that lets us derive every single one of these transport lemmas in constant time. All right. So we at the top of our proof, we add a structure that is say n log n lines. All right. And then with that structure, it magically makes generating these transport lemmas constant time. All right. Okay. So their idea was given a proof, you turn it into this tree here, right? Um, and then what do transport lemmas look like in this tree? So let's say that this node here represents the context A comma A implies B, right? Because it has a parent node that has A as an assumption and so on. So what these transport lemmas look like is they, for this, here's an innocent looking example of what transport lemmas might look like. So let's say that this guy here is gamma 0, and this guy here is gamma 0 comma gamma 1, right? So if we ever need a transport lemma for this node here, it's going to look like this. It's going to be of the form um, from gamma 0 and gamma 1, um, we can get gamma 0. Right? And this is just a tautology, so we can prove the single step pretty easily. Right? But what about for multiple steps? Let's say that this node here represents gamma p, and this node here represents gamma. So for this transport lemma, it's going to look like from this bigger context with more assumptions, um, we need to show um, the conjunction of this smaller context with fewer assumptions, right? Does that make sense?
Yep.
Okay. All right. And here's another example. Um, I think my goal here was to show the apply rule and how you could show these two. But anyways, um, so what's interesting about these transport lemmas is that you can compose them because this happens to be a tautology. So if you have A implies B and B implies C, then A implies C. So this is something you can prove. Um, so if you have two of these um, transport lemmas and they line up, then you can compose them into a bigger transport lemma. Does that make sense?
Yep. This is reminiscent of like skip lists. I forget the name for it. Is skip list the name? Like where you have like a linked list, but there's like skipped items in it so that you can traverse it more quickly. Seems vaguely similar.
Yeah, yeah. Um, that's pretty much the structure we're going for. Okay. So what we need is we need to come up with uh, a set of proofs, or sorry, we need to come up with a structure that lets us prove any transport lemma in a constant number of steps. So what the paper links to is um, a so this basically reduces the problem to solving what's called the transitive closure on trees problem or whatever, where you want to calculate these jump lists, or sorry, you want to find a set of these edges here, these back jump edges, that let you construct any of the back jump edges in a constant number of steps, specifically just one composition, right? So if you look at this structure here, let's say you computed all of these edges and you want to go from this guy to this guy. You can do it in one compose step. Right? You compose this arrow with this arrow. Does that make sense?
What if you're trying to go from somewhere on the left side to somewhere else in the like? What if you're trying to go from the if we zero index it from the left? Let's say you go from 3 to 0. Wouldn't you need two compose steps?
From 3
Yeah,
to 0.
yeah, 3 to 0.
Right. So this isn't all of the edges. This is just a suggestive subset of the edges. Um,
Okay.
so we can't get with just these edges. We can't get from say 3 to 0 in one compose step. What we can do is we can get from any node on the right here to any node on the left here in one step. Okay.
Yeah, I'm with you there.
All right. So the trick is you just apply it again. So at this level, we add at most n edges, right? It's kind of like a you kind of do a recursion, right? Where you break your big stick in half, and then you do the same structure on each of the halves, right? Um, and you keep doing that until you get down to the base case. So for every one of these layers here, let's say that um, the white ones are the largest layer. You add at most n arrows to your graph, right? And if you construct them in the right order, namely, if you do this single step and then you compose it with this single step, you can get all of them in uh, at most n applications of our base rule, right? Um, and you recursively divide um, this big stick in half, and you do the same thing to each one of these left and rights. Eventually, you get down to a level where everything is just one step, right? So you have to apply this halving process log n times, and then um, yeah. Does that make any sense?
Yeah, so the total amount of arrows you're going to get out of there is n log n, right?
Yeah, yeah.
There's the
So
n
with
levels
n
of
log n
depth and
arrows,
or sorry,
do you agree that
sorry, go ahead.
right, do you agree that with n log n arrows, you can get from any node to any other node in just one composition step?
I would have to like work out the off by one error like possibilities and convince myself that if it's like not a power of 2 then that's the case, but yeah, it looks like it's on the order of n log
Yeah,
n. I
it
would
would be
definitely
a
agree with you
big
of
O.
big O of n log n. Yeah, I'd
Yeah,
bet
yeah.
I'd bet my life for $1 on that right now.
All right. So that's for the stick case. Right? What about for the other case where it's a tree? You can do a similar thing where you split on the depth, all right? And you jump up to the split, and then you jump from the split to uh, each of the parent nodes, right? If you do this for a completely balanced tree, um, you get something that looks like this. Sorry, your top subtree has square root of n nodes, and each of the bottom subtrees has root n nodes, all right? And there's root n minus one of them. Do you agree with this tree setup that you get by splitting it down the middle? All
Yes.
right.
Wait, actually maybe not. Are these all like big O order notations? Because like I'm thinking like if we cut it in half, then there are root n. There's not exactly root n things on the bottom layer, right?
On the
Because
bottom layer,
is
um,
root n the amount of nodes in the top of the tree, or is that the amount of leaves in the top of the tree?
n is the number of nodes in the entire tree.
Right, but I mean root n up there should be the amount of nodes in the top half of the tree. So
Yeah.
then, but the amount of leaves should be half that, assuming it's like a binary balanced tree.
So the number of leaves. Let me think. Um,
Like if it's a balanced binary tree, like the top of the balanced binary tree, there should be like roughly there should be one. What is it? Like the ceiling of half of the amount of nodes in that top section of the tree is the amount of leaves that it has.
mm,
It's like
so with
it,
n nodes, I think you get uh, So 1, 2, 3. Okay. So let's say you have these three nodes here.
Yeah.
You always get n+1 leaf nodes.
Yeah, exactly.
Yeah.
So like in that case, like I might be nitpicking. I don't know if you really meant to be as serious as about this as I'm making it sound, but like so like if we take the case of like let's say a depth 4 binary tree and it
Yeah.
just splits so you'd get what 16 total nodes. Like the top half is going to end up with 3 of them, right?
Yeah.
But there's only 2 leaves on the top
There's
half,
only two leaves.
right?
Um, so the leaves would actually be the leaves of this node here. So it'd be these guys, I think.
Uh is that right? Yeah, you might be right.
I don't know. Just
Mm,
assume I mean big O.
yeah, okay, yes, sure. Then I agree.
I'll just wave my hands and pretend. All right.
Yeah, I mean, where I was going with this was like, the triangle on the top has root n nodes, but it has less than root n leaves. Um, so that means that the amount of bottom triangles that you have there is like half of root n, and so that the total amount of nodes in the tree would then be like half of root n times root n plus root n, which is like half approximately half of n, so you derive a contradiction. But anyway, I think I'm nitpicking on something that maybe you didn't need to be very serious about.
Yeah. Anyways, I claim you can split a balanced binary tree in this way, where you split it in the middle and you get approximately root n nodes at the top and a bunch of subtrees that have approximately root n nodes. All right. So what you can do is we need to draw these arrows where from every one of these nodes we jump up to the cut. All right. So if you jump from this one of these subtrees to the cut, um, how many arrows do you need? You need root n for this one subtree, and then you have root n+1 um, subtrees total, right? So you need about this many edges if you just want to jump from the bottom subtrees to the cut, which is on the order of n. Okay.
Yep, makes sense.
All right. And then the other part of um, our structure is we need to be able to jump from the cut to any node above the cut. Right. So if you look down here, how many leaves do we have? We have about root n+1 or something like that. So from these root n+1 um, uh, leaves, we need to jump to each and every one of these. What do they call it? Each and every one of these parent nodes. All right, and there's at most root n of those. This is a extreme overestimate, but anyways, it still gives you big O on the order of n. Okay, do you agree with that?
Yeah, I think I see where you're going with this. So like every bottom node teleports to the leftmost uh what would it be? The highest level node which is left of itself and under the cut point. If I hope I'm getting that right. If it's under the cut point, and everything above the cut point would then just be like strongly connected, like
Yeah, so
leftwards.
like for this subtree here, we need
Yeah,
to be able to jump to this cut point from anywhere below it, right? So you need to add an edge from here to here um, for every node in the subtree. And there's about root n of them, right? And then from this leaf here, we just need to jump to each of its parents. So you can get anywhere on this path,
yeah.
right? Anyways,
Doesn't this do better than O log n?
this is an overestimate.
Well, no, but like
So
wouldn't that be O of n? Maybe I'm missing something. we're also
So this is for,
sub-recursively doing it into
yeah,
each tree. Okay, yeah. We still have the recursive structure, so you get log n.
we still have to recurse big O of log D, where D is
Right.
the depth, right? But an overestimate for the depth is the number of nodes, right? So big O of log D is big O of log n. So
Wait, no, that's not true. I mean, if it's a balanced tree, that's it's O of log d is O of log of n, right?
yeah, yeah. No,
So I
it's
think
an
you're.
overestimate, but it's good enough. All right.
Well, yeah, but that's
So this
not
shows that,
equal. I mean, yeah, like, yeah, yeah. There you go. No other way. Yeah, good.
all right, all
Now
right.
I
So
agree.
that's good enough. So what that shows is if we add um, big O of n log n, or sorry, if we construct big O of n, we only need this many edges. This is how many we need to store. Um, if we store this many edges, then from anywhere in the tree, we can jump to anywhere else in one composition. So that's the property we needed. Okay.
That's sick.
So this is what they called the, actually have that open somewhere. Um, the serial transitive closure problem for trees. They actually prove a stronger version of this that gets you uh, n times the inverse Ackermann function of n, big O of n.
Whoa.
Uh,
How on earth do you do that?
yeah, it's a bit more contrived, but n log n is good enough for my use case.
Cool.
So, anyways,
Wait, so
um,
one thing I'm missing here was your idea between the tree and the line. Are those representing the same structure? Like you drew the thing with the line there that you're
yeah.
drawing
So
left.
this is like a special case of this tree here. Okay? It's a special case where you just assume everything you need in one straight line.
Right. But in the bottom case, that's what we have in real life, where we've constructed that tree as we read in our prefixes.
Yeah.
Um,
What's interesting is if you're gonna do a proof checker, you don't actually care about the whole tree at once. You only care about one path that you traverse down. So, for example, this one.
right.
Um, so um, you can like do this cool memoization trick where you only store the edges that involve these guys,
Uh huh.
the parent.
Yep.
All right. So
Yep.
you memorize this, and then whenever you need a uh,
Like a full path back, then
yeah,
you have
whenever
how.
if you need a transport lemma, you only calculate the edges that are in this structure here, and if you calculate them, then you store them.
Hmm.
And you never have to do more than this amount of work to prove the statement or whatever. All right. So now I would like to give an effective method for finding the cut.
Sorry, I also just realized that Multitube posted a question like 10 minutes ago.
Oh yeah, you
Just
did.
checking to what extent I'm following correctly. We'd like to prove lots of these tautological formulas, but there's O of n of them, and the paper would like to bound the total number of lines used. Yeah, using the Ackermann function. I think you were about to go into that, but to reduce this, the paper forms the distinct conjunct gamma tautologies into a directed tree where gamma 1 has an edge going into gamma 2 if and only if gamma 1 extends gamma 2 by one element. Then the aim is to prove the tautologies. I think that matches my understanding of what you've said so far.
Yeah, something like that. All right. I can link the papers if you want to read them later, because
Yeah,
I'm
that'd be
not doing
cool.
a very good job of
No, no, no,
explaining
no,
this.
no. You're
All
fine. I just had to
right.
get over a little hump of like understanding the terminology and notation, but
Yeah.
I think I get
Um,
it.
so, anyways, the next thing is how do you find the cut? So this is our cut here.
Mm-hmm.
Obviously, you don't want to walk the entire tree to figure out where this cut is.
Wait, is the
And
graph going to be balanced in practice?
No, not really.
Oh, okay. Then I take back what I said about it being O of log of n, because that, if it's not a, yeah, if you got a
Yeah.
bad
In the
guess.
in this special case where you have a stick, which is this guy, it is straight up just sorry. Uh, log of the depth is the same thing as log of n in this special stick case. There
Yeah,
you go.
right. In a balanced case, you get log of d equal, or you get O of log d equals O of log n, but in reality, you're probably going to be somewhere weird in between.
Yeah.
Yeah. Okay, makes
All
sense.
right. So the next problem is how do we find the cut? Um, so for this case, if you just have a big stick, you can just divide it down the middle, right? Well, actually, when we recurse into these left and right subtrees, um, you have to do it again. All right. So it's a little bit more involved. Sorry, finding the cut is a little bit more involved than you'd expect.
When you say finding the cut, you mean finding the optimal cut to minimize the amount of edges?
What I mean by finding the cut is, I mean, if you have two contexts where this guy is a subcontext of this one, and you want to find the cut that lets you
Oh,
construct just one more arrow between them,
so given the
right?
given the structure of arrows that is already present, how do you know which cut to use in your composition?
Yeah, which cut has the two arrows that we need
Gotcha.
to compose to get the single jump, right? So in general, we can assume we know the which contexts we want to jump between, right? Because we get them for free out of our sorry, the the proof we're trying to transform tells us which contexts we need to jump between, right? We need to go from these contexts that we need to jump between to this cut. We need to know where the cut is. That makes sense?
Yep.
Okay. How do you go? How do you figure out where the cut is? Um, so here's a suggestive picture. Let's say we wanted to jump between red and blue. If red is at depth 3 and blue is at depth 4, we want to use this cut here, which is at 4. So we want to jump from blue to 4, and then from 4 to 3, and we want to compose those. But for this other choice of two contexts that you want to jump between, um, you want to jump from 3 to 2, and then from 2 to 1, and then compose those. So the cut for this guy is 2. Um, yeah, does that make sense?
Yeah, it looks like there's some like binary and under the hood going on here where we like do like,
Yeah.
or maybe in just like find the leftmost bit. Yeah,
Yeah.
yeah, there you go.
So
Two to the
this
k.
is my suggestion of what the cut is. We want to find the largest 2 to the k such that there is an n where a is less than or equal to n times 2 to the k, which is less than or equal to b. And why do we need this n? Um, well, here's an example of why we need the n.
I think just to put that in other words, you're saying just to find the biggest bit which they differ on. Is that right?
Yeah.
Okay. Yeah.
Okay. So first thing to notice is that b minus a is less than or equal to 2 to the k plus 1. Right? And why is that? Well, assume they're different. All right. So let's say this is the largest cut. Uh, assume this is the largest cut, and then assume the distance between A and B is greater than 2 to the k, which is this cut. Um, then you end up with a picture like this, where you have a bigger cut, which breaks the assumption that this is the biggest cut. That makes sense?
Sorry, say that again.
All
Were
right.
you
So
trying to show
notice,
why n matters? Yeah, yeah. So the green line is two times the lower line, so we can't include multiples.
yeah,
I think that's what you're saying.
yeah.
Okay.
So if we assume that there is a sorry, if we assume that 2 to the k, which is this line here, times n is between a and b, right? And this k is sorry, this 2 to the k is the largest one that has this property. Um, if we assume that the difference between b minus a is greater than or equal to 2k plus 1, which means you have greater than this guy between them, it breaks because you get a larger cut. Does that make any sense?
Yeah.
Okay, we'll go with that. So if you just write that out, you end up with this mess, which says there exists an m such that m times 2 to the k plus 1 is less than or equal to a, um, and a is less than or equal to b, and b is less than or equal to m plus 1 times 2 to the k plus 1, which is this guy. Um,
I'm liking that claim.
anyways, here's my claim. The cut is at this spot here, where you just take a XOR b, and you take the most significant bit of that.
Yeah, that makes sense.
So that's how you
Biggest
find the
binary
cut.
number between the two. Yeah.
Um, and so this paper here, where's it at? The serial transitive closure problem for trees. It doesn't give you a an algorithm for solving the transitive closure problem. It just says that you can do it um, in this number of edges, right? So that's why it was necessary to come up with an algorithm that lets you do it quickly, which is this part.
But correct me if I'm wrong here. We haven't gotten to the Ackerman thing, right? Is there some trick beyond this?
There is a trick beyond this that lets you get a better bound, a tighter bound than n log n. But I couldn't think of a effective algorithm that tells you where to cut the tree.
They just suggest that there is a tree.
Yeah, they just show that there is a set of edges
I
that
see.
has the property we want. They don't explicitly tell you how to construct that set of edges,
Huh.
but there is one. I just don't know what it is.
So okay, we just don't know how to find them. Okay.
Yeah.
Interesting.
All right. Bonus content. What can we use this for? Um,
I'm also
where
really
was I?
curious to just try it in like the small finite case example where you just have like a nice well-behaved tree and you just have to find like a minimum integer number of edges instead of doing the large case. I'm curious to actually just try that out by hand.
Okay. So, in general, if you want, if you just construct every possible one of these transport lemmas, you need on the order of n squared edges. Okay. Why is that? Because you need to jump from this guy to every single one of the previous guys. So this is n times n minus 1, and then this would be n minus 1 times n minus 2, and so on, all the way down. Right? So if you wanted every single edge,
No,
there
no,
are a
no.
big O of n squared of them.
I mean like with composition, composition. We're still allowing for composition.
Yeah, yeah.
Um, yeah, I'm gonna try that by hand right now. I'm gonna like take your little tree there, like the tree that's right below that, and see if I can figure out like a smaller number of edges than that algorithm gives us.
Yeah. According to the paper, there should be a few assignments, or sorry, a few sets of edges that are smaller than the one that I showed exists, but yeah, I don't have an algorithm for finding that. Um,
You don't happen to actually know the number, the minimum number, do you?
no, I don't.
All right, I'll hopefully find it.
Okay. So what else is this proof that you can that any proof written in a nested deduction system can be simulated almost linearly in a Hilbert system? What else can you do with this proof here? Well, if you look at the simply typed lambda calculus or just the normal lambda calculus, um, here are the type deduction rules for simply typed lambda calculus. I'm sure you're already familiar, so I'll just skip that. Um, Notice that a Hilbert style system has a bunch of similarities with the simply typed lambda calculus. For example, you can define this combinator K here, where um, it has this type signature, right? Which is it's a function from A to functions from B to A. Um, in this Hilbert system that I showed earlier, we have an axiom that says you can't assume, sorry, um, you can prove that A implies B implies A. So that's interesting. This type signature looks a lot like this axiom here. And this application rule looks a lot like modus ponens here, right? Yeah. So QSwap's already guessed where this is going. Bracket abstraction. So in the simply typed lambda calculus, you can come up with so for every well-typed function in the simply typed lambda calculus, you can come up with a composition of these two functions that gives the same result for every input. So they're like the same function up to extensionality, I think. Um, and here's an algorithm for doing that. This algorithm is big O of n squared if you do it the naive way. Actually, there's a bunch of extensions of this algorithm that are slightly better uh, in that they're not big O of n squared for some cases, but anyways. Um, so with this bracket abstraction algorithm, the goal is to turn a simply typed lambda calculus term into just S and K, right? But this algorithm that is well known is terribly slow at big O of n squared. And it turns out you can use an idea similar to what's in the paper to make a algorithm that's just straight up big O of n. Is that interesting?
That is cool. I did not see this coming. Is this a new result?
Is it a new result? I don't consider it a new result, but it, I think of it as just an application of the Curry-Howard correspondence. I think is what they call it.
Yep. Yeah. Um, but I mean, like finding this algorithm that packs things into like SK calculus, a small like a small term.
There are other algorithms for bracket abstraction that get you the big O of n log n bound, but uh,
The O of log n one is new.
uh, they also so I do think this is new. Yes.
Okay. Cool.
Um, would you like to see an explicit construction of that algorithm?
Absolutely.
Absolutely. I did write it out once, not very effectively. Okay, so the what the paper said to do is it said to package together So if you look at this through the Curry card correspondence, oh man, this context here, you can think of these as bound variables in some scope, right? And what the paper said to do is to package these together into a list, right? So you can take all of these uh, you package all of these bound variables into a context, which is just a list of all of the individual bound contexts, and then that's what you feed through your combinators. Um, yeah. So
What do you
what
mean by
this
feed through exactly?
yeah, so what this S combinator does here, um, you can think of it as taking two functions x and y, and then this third z here, you can think of that as the context where you have all of your variables, right?
Mm-hmm.
So this is a list of bound variables, um, and what this S, you can think of this S combinator as just feeding your context through your combinators, if that made any sense.
Okay, yeah.
All right?
And then you compose them for a reason that I don't know.
Yeah. Yeah. Um, mm.
X. Wait, hold on. I'm staring at. What is the bottom here supposed to be like? What are the bottom three lines here supposed to be used for? I see your
So these are
equation.
just equivalences. So
Why do we care about them?
why do we care about them? So notice that this function is essentially the same thing as this function.
I
Why
think
is
that.
that?
Hold on, wait. Let me try and do this in my head. Um, lambda x. I guess we're assuming that x is free in M and or there are no instances of x in M and N.
There could be
Or there
for
could
the
be.
stop ruling. Yeah.
Okay. I think I agree.
Okay.
Why
I
do we care
would
about
type
this?
it out, but my keyboard isn't working anywhere.
Oh, that's okay. Well, why do we? But what's important about these three identities?
They let you transform any lambda calculus term into just S and K.
Oh, sorry. I see. That's a. Uh, you have an. Wait, no, I don't see. You have. Are you just implementing the three rules of lambda calculus? But you're always putting a lambda x on the left side. So up to eta
Yes.
equivalents you get.
So any combinator, sorry, I didn't specify.
Yeah.
Any combinator in the simply typed lambda calculus, you can write in terms of just S and K,
Yep.
or compositions of them. Okay. So they have to be closed terms.
Right.
Um,
Right. Okay. So yeah, so you're introducing the identity as a way to introduce like x as a variable, and
yeah,
then you have composition, and then abstraction on the bottom. Yeah. Okay. I get what you're doing. Cool.
yeah. So this is the classic algorithm for bracket abstraction.
Yep.
These are strict equalities, like um, this side is beta convertible to this side or whatever,
Yeah.
by just following the rules of simply type, or sorry, lambda calculus. Um, but it also turns out that these equalities are enough to make an algorithm for converting any lambda term into just S and K. Um,
Right.
so if you have something of the form uh, lambda x m applied to n, you replace it with this side, but you also recursively run the algorithm on
Mm.
these two subterms. That made any sense.
Yeah. Yep. Yeah, that makes sense. Why is that slow? You're saying that, or you're saying that would generate something that's larger? Is it just because we're packing x's all over the place, or is there somewhere fundamentally that that's going to end up being less efficient?
So the reason this is big O of n squared instead of something nice. So for this step, we only make the original expression a constant amount longer, right?
Mm-hmm.
And for this step, we only make the expression um, well, we also have to.
It's also constant length, right? I mean, you're only sticking a k on every time that you do a like an abstraction.
Yeah. Let's say that we only have one binder and it's X, then if we follow this algorithm, we'll make the term a linear amount longer, right? Because we only have one binder and it's X.
Uh huh.
So eventually, these compositions of
Terms.
maybe I should just link Wikipedia for this. That'd probably be good.
May, are you saying the first thing is like the fact that we have to recursively do something to the first thing is going to make it longer? I'm misunderstanding how that's the case.
All right. So I claim that this is a big O of n squared algorithm. If you just implement it as written. Um,
I don't see why. It looks linear to me.
it does look linear.
Like at each step, like all of like in lambda calculus, you can just count the amount of terms that are in your like count the amount of things that happen within your expression. So like a thing happening being either introducing a variable, using an abstraction, or using an application. Um, and it looks like in the abstraction case, you're just adding a constant k combinator everywhere. In the variable case, you're just adding a binder everywhere, and in the application case, you're just adding like an s combinator and two binders.
um, yes, but that's if you just have the one binder. If you have multiple binders, then it.
What do you mean by when you
I'll
have
get there.
multiple? Oh wait, are you saying you have to for every binder that's inside of m and n, you have to put the binder on the outside, on the top?
All right. So here are our three equivalences.
Yeah.
So how do we define an algorithm that does bracket abstraction on these? Well, so let's say bracket of lambdas means do bracket abstraction on whatever's inside of the brackets, right? So to bracket abstract xmn, what you do is you yeah. So if you want to bracket abstract a application of m and n, then you just do s applied to bracket abstract this, applied to bracket abstract that, right?
Okay.
All right, let's follow our algorithm for this case. Well, okay.
I just had a network hiccup. There's
Or
a
maybe Ben has a bad example.
I suddenly can't see your screen.
That's a good sign.
Can others?
Let me
Now I see it again. I hope I'm not derailing you too much. Did you like?
I did intend to talk about this. I just
Okay.
didn't think about it very much. Um,
If you're sharing your screen with something, I can't see it. I can only see Discord.
I picked the wrong. Good.
All right. Yeah. So bracket of uh, bracket of yeah. That looks like the same as before.
Yeah. I'm trying to find the counterexample that shows that this is big O of n squared. In the worst case, there is one somewhere. I just don't know where it's at.
And to be clear, where you're saying big N squared of the amount of terms in the resulting thing, not big N squared of the amount of time it takes you to write it.
Yeah. So like, if the size of the original term is n, then the number of s and k combinators in the bracket abstracted term is at most big O of n squared.
Huh.
Um, for this algorithm, at least. Um,
Okay. Am I being dense here? Can someone in chat give me like a thumbs up on if they agree with me or not for thinking intuitively that that should be linear? That feels like it should be linear to me. No responses. Because like I would imagine like the amount of bracket abstraction things you're going to like the amount of steps that you're going to have to do is equal to the amount of like terms in your original expression,
um,
and also the amount of s and k things that you introduce each time is linear as a function of the amount of times you do the like a bracket reduction. So like therefore, if I'm not missing something, like you have to.
so when you push this bracket x down the tree,
Yeah.
right?
Yeah.
Um, so if you just have one binder, bracket x,
Yes.
you have to push this bracket x all the way down to the leaves, right? So if you have a tree with n nodes, there are n plus one leaves. So
When
you
you say
get,
you have to push it down to the leaves, what do you mean by that? You have to
what do I mean by that?
each leaf in
Um,
there.
so if you have bracket x over m and m contains x,
Yeah.
um, then you have to apply these rules again, right?
Yep.
So if it's this case, you stop. If it's this case, you replace it with skk,
Yep.
right? But x has to be a leaf. So you stop when you get to a leaf, or you stop when you get to a term without x.
Yeah.
So
Yeah.
these are
Yeah.
the base cases. Um, in the other cases where you have a branch in your tree, a node with two children,
Yeah.
you have to push the lambda x over each of the children, right?
Yes.
So um, you have to push down this lambda x to the leaves. Yeah.
Yeah.
So
Like as
if
in
you just have one
the
binder,
immediate children, not
um,
the leaves of the expression.
right, but your immediate children either don't contain x. Sorry, if they're leaves, uh,
Like wouldn't like maybe are you suggesting that a worst case thing would just be like a ton of like abstract like or sorry a ton of applications like if we do A B and then C D like this like if this is our lambda term or blah and each of those you can just say is the identity or something um, for like lambda A equals A etc.
yeah. So since you have an application node, you gotta split this lambda x to both of these cases here, either
Yep.
side, right?
Yeah.
Um, and you have to keep doing that until you get to these leaves here. Yeah.
Yeah. Yeah.
Each one of these is an app node.
Yep.
Um, so eventually, at the bottom of your tree, you're gonna have lambda x whatever at each of these leaves, and there are if you have n nodes, there's n plus one leaves.
Yep. Wait, no. There's n over. How do you arrive at that? The amount of the leaves are a subset of the nodes. Or you mean
Right.
non-leaves? If there's n non-leaves, then there's n plus one leaves, assuming a balanced tree. Is that what you're saying? I think that's what you're saying.
So yeah, if you count these as your nodes,
Yeah. Okay.
there's
Yes.
three nodes.
Yep.
Then there's n plus one leaves. Yeah.
Yep.
So you have n plus one instances of x. So in the case of just one binder, you make the resulting tree linearly larger. So like,
In the case of one binder.
yeah, this one binder here with just x. Yeah.
Yeah. Uh. Well, no.
Because yeah,
Oh. Wait. When you say push it recursively down, what do you mean by that? Are you saying like the
I
lambda
mean,
x gets
apply this rule here.
right, but the lambda x only gets tacked onto the two children. So
Yes,
like
but
doing
then
that
you
once
do
doesn't
bracket abstraction on both of the two children.
right. Yeah. But so like through all of the bracket reduction or what is it called bracket abstraction steps throughout the whole tree, you're only at most going to be appending one lambda x to each node in the entire tree.
Yes.
So that should be constant, right? Or sorry, that should be
Uh,
linear. I mean, that should be linear as a
yeah,
function of
we
the
go with
amount of
n.
yeah. You've
But
appended
that's for one binder. If you have multiple binders, um, they also have to do at most n, right?
when what do you when you say binders? Do you mean instances of application?
Instances of bracket abstraction on lambda something dot mn. Like,
Yeah, yeah. So
so this would be a binder. This would also be a binder.
oh, I see. Okay, I get it. Never mind.
Yeah. So for every
Okay,
binder,
so
we have
it's
to
going
do
to
linear
eventually
operation.
flush down to all of the leaves each time you have a binder at any recursive subdepth.
Yeah.
Okay. I'm with you now. I didn't get the mechanic.
Yeah. Okay. So this algorithm is big O of n squared because um, you have to take every binder down to the leaves, right? And there are at most n binders. that's the that's the reasoning for it being big O of n squared.
Okay, sorry for the extremely long tangent. That was just me not understanding how this works.
I'm also bad at explaining things, so okay.
Perfect duo.
So that's the default algorithm. I did write out the linear algorithm. Um, I'd have to go grab my laptop.
Is it just invoking the thing that we said before, basically? Like,
Yeah, pretty much.
cool.
So the idea is you make a structure that's almost linear in the size of your tree that
Mm-hmm.
lets you transport something in constant time.
Gotcha.
In the case of lambda calculus, you can actually do it in the linear space. Um,
Yeah, what's the difference? Why do we get linear in lambda calculus as opposed to like that weird um, Ackerman thing?
um, because in lambda calculus, there's less structure. You just have to be able to jump up however many binders. You don't care about the types. So,
Oh,
right. So in this tree, if you're in this subtree over here, um, this edge and this edge here are different, right? Because they have different types at each of these nodes. Yeah.
yep.
But in the case of lambda calculus, or sorry, on-typed lambda calculus, where there aren't types, these two edges are the same edge.
Okay. Right. Yeah. You can use the same lambda calculus construct to get from both edges to their parent.
Yes.
Okay. So you can save edges. That makes sense.
All right. So how do you set this up? I define P like this. It's the paired combinator. Right. Just the Scott encoding for the pair combinator. Um, you need the unpack combinator. I should probably just go look at that joke. So instead of using and, we're using pair. That's the first difference.
Multitube asks, is it correct to say that a lot of the waste of the naive algorithm is due to repeatedly rescanning large sub-expressions to check whether a variable occurs freely within them? Um,
Yes, that is another problem as well.
I think that's not the problem that, at least that's not the problem that I eventually came to understand, which was if you have two binders outside of an abstraction, then like or more than two, each one of them is going to get multiplied by the amount of leaf nodes that is underneath them. So, like in the worst case, if you have like maybe half of the things that like half of the characters, just to use an arbitrary metric, half the characters in your lambda calculus expression are like being used for applications and half of them are just used for tacking on random useless binders outside of them, like that half of the amount of binders is going to propagate down to um, each leaf of the large structure of applications. And for that reason, you're going to end up with like, using that example, it would be, you know, I don't know, you would end up with like the half times the half, and then I think you divide off another term for like the quantity of leaves in your tree. But does that make sense? I think what you're saying is also true, that like you also have to start to repeatedly rescan things, but that's like a
Yeah.
computational problem, not a
Um,
size of the written answer problem.
the way I avoid the check where you have to look for E in or whatever is I just omit this step entirely. You only need the first two rules really. because you're gonna have to walk the tree however many times anyways.
Sorry, wait. How can you just omit that?
How do you just omit this? Instead of checking if X is free in A, when A isn't a leaf node, uh, you just don't.
Wait.
Because this is a special case, all right? If A isn't a leaf node, then it's of the form MN, right? In which case you do this. But if it is a leaf node, then you can do this. Only do this when A is a leaf.
But A can be. But A can be. No. Wait. No. Because A. What if A is like lambda y dot mn?
Lambda y dot mn. Um,
Like the first bracket in the top left of your paragraph there, but replace the x with a y. Then it's not a leaf.
sorry, I missed another case, didn't I?
Multitube says, so each outer lambda is making the algorithm run over the same leaves an extra time. Exactly. Yeah, so you would like if there's like 5 binders on the outside and then a big tree, then each leaf of the big tree would then have 5 binders applied to each individual leaf. So you get like multiplication between the amount of binders and the amount of leaves. Okay, at lambda x. Wait, is that a rule? That wasn't in the website you showed just a second ago.
um, let's see here. It's not on the website, but
Also, that still doesn't handle the case of what if you then have 3 lambda brackets applied. Lambda, what are they called? Lambda.
I think how do they manage that case? Let me think about it. I can't read Haskell, so that's a good sign. I think the idea here is you just recurse down a term until you get to something with only one binder, right? And then you apply this. Yeah.
well, like so, like I would imagine that there has to be another entry here in this list that says like lambda x dot m where x is in m, right? Because we've covered all the cases except for that one. Wait, yeah, stay there for a second. I'm not. I've written some Haskell before, but this is above my pay grade. Hold
Yeah.
on. Let me wait. No, stop. Don't move. Uh, yeah, no, I don't know what this is saying. Lax XM?
Um,
Maybe that's yeah. Maybe lax is saying it's a free variable. Also, just
maybe
FYI,
this
I
guy
probably have
tells
to
you.
go in like 15 minutes.
Yeah, here it is.
Oh, oh, okay, gotcha. So yeah,
Yeah, so this is enough to remove one variable. If you want to remove all of the binders, you have to apply it multiple times.
is it not saying that this is a different approach though? Multi-sweep variety. What does it mean, variety?
Um, what does it mean by variety? I think it's just referring to this algorithm here.
So there's like 2 different algorithms that you can apply, and one of them.
Oh, there's a whole bunch of
Oh
algorithms, but
God.
most of them aren't linear.
I see. Huh. Okay. Sorry for sidetracking. Anything
It's fine.
else? You got anything else? If not, I might drop soon here.
I was gonna write out the rules you need to do the linear algorithm, but it might take a while. So
What are the rules?
what are the rules? I have to define like what is that? 7 combinators, and then
Maybe
the
separate
transport
talk.
separate talk.
Maybe you
Maybe.
should just do one on SKI calculus.
Yeah, yeah.
If you don't mind. I don't mean to put give you work, but that'd be very cool. I haven't given
Yeah, maybe
enough
I'll figure out
attention.
how to explain things better then next time.
No, I think this was good. Just took a little bit of time to get over the hump of like figuring out all the like the tax and the what are they called? I don't know, notation. Cool.
There isn't too. I didn't think there was too much notation, which is why I
Yeah, well, I mean,
tried to cover.
it's just dense. Like I think on a couple of the slides there, it's just there's like big chunks of like implies and stuff. I mean, I think it was fine, but
Uh,
I eventually figured
yeah,
it
yeah,
all. Yeah, like all that, like that's not immediately parsable in my head. But no, I think that was fine. I got the gist. So I appreciate it.
yeah.
Thank you for the talk.
It isn't terribly difficult to write proof checkers for these either, and you can extend them to they call first order predicate logic,
Oh,
and then do ZF set theory.
sweet.
Yeah,
Do you do lean? Do you
all
know
right.
lean?
Yeah, I do.
Oh, cool. That's on my list
Not
of
very
things to
much, but
learn.
it's not too terrible. If you have some background in dependent type theory.
Okay. I don't think I do.
Yeah,
All right. I'm gonna peace out.
yeah.
Thanks for the talk.